I'm going to walk you through the lab materials for Lab 6 on 3D Worlds. Okay, so first go to the GitHub, download and build the project file, and I've already done so. And if I just run the code, you can see we have our create texture map as we've used in Lab 3, and it fills the screen. Okay, so with Lab 6, what we're looking at is we're looking at the building of the 3D worlds and also how we view the 3D worlds through the camera. Okay, so I'm just going to bypass some of this material here, which you can read at your own time. I'm just going to focus on this figure 6.3 here. Now, it's important that you're aware of these four spaces. Okay, so we've got the object space here. Now, this is a space in which the object is defined, and usually objects are defined with their center of mass at the origin 0, 0, 0. Okay, now each object, which will form what we call the world space, is transformed using translation, scaling and rotation transformations, which we covered in Lab 5, into the world space. Okay, so here we have the world space. We have two simple objects in the world space. Now, if we were to view this world space from a camera, okay, so we stick a camera in the world space. You can see in this particular diagram we have it pointing down the y-axis. The next step is to transform the world space to the view space. Okay, so I should have mentioned, but to go from object space to world space, we form what we call a model matrix, and that's a combination of your translation, rotation and scaling operations. To go from the world space to the view space, we have the view matrix, and what this does is it puts the camera at 0, 0, 0, pointing down the z-axis. So here we have, you can just see the x and y axes. That's because the z-axis is pointing out of the screen towards you. Okay, and from the view space, we finally go to the screen space by use of the projection matrix, and this allows us. This essentially is what we see on our final OpenGL window. Okay, so we are concerned in this lab with calculating the model, view, and projection matrices. Okay, so to start off with the model matrix, I'm going to grab some code here. Okay, and I'm just going to paste it into our main.cpp. Okay, in the render loop. So I'm going to scroll down. Now remember, the render loop is this do while loop here. Okay, and just before I draw the triangles, I'm going to paste in the model matrix. Now let's have a look at this. Okay, so first what we have is we have a float which gets the current time. This is going to be used to animate our object. And we have translate, scale and rotate matrices. So these use the GLM versions. Okay, so the first one will translate our cube object so that its center is at 0, 0, -4, so it's essentially moving it down the z-axis. The second one will scale it by 0.5 in all three directions, so that's halving the size of our cube. And the third one will rotate it. Now the rotation angle is whatever time we're on. Okay, so that's this float up here. And the rotation vector is 0, 1, 0, which is a vector pointing straight up. So it's essentially rotating about the y-axis. Okay, and what we've done here is we've calculated a 4x4 model matrix, which is the scale multiplied by rotate multiplied by translate. And remember from Lab 5, we read these from right to left. So scaling was applied first, then rotation, then translation. Okay, so that's calculating the model matrix. The next matrix we want to calculate is a view matrix. Now we want the camera to be at 0, 0, 0 and looking down the z-axis, and to do so we combine two transformations. We first translate wherever the camera position is to the origin 0, 0, 0, so that's a translation by minus camera pos, and then we align the space so that the camera is pointing down the z-axis. Now to do so, we have three camera vectors: camera front, camera up and camera right. Okay, so they point to the front, up and right respectively. And we also have a world up vector which is just pointing straight up in the world space. Okay, I'm not going to go through the derivation of these, but you can see that here's a translation matrix by minus camera pos, and we also have an alignment matrix. So if you want to see how these are derived, you can read through this content here. So what I'm going to do is I'm going to grab this code, and this code calculates the view matrix. I'm going to put it into our render loop just after we calculated the model matrix. Okay, so here we have the camera position, target, and world up. So our camera position is going to be positioned at 110. The target is going to be the center of where we moved our cube. So we moved our cube to 0, 0, minus 4. So it's looking straight at the center of our cube. And world up is almost always 0, 1, 0. Okay, then we calculate the camera front and camera right and camera up vectors. And then this is just defining the align matrix as an identity matrix. Okay, and in this for loop, I've just essentially defined the translate and align matrices. So if I quickly go back, the alignment matrix. So the first column is camera right, second column camera up, etc. And you can see that's what we have here. Okay, and the view matrix is translate first, followed by align. Okay, and if I multiply by the view matrix, you can see. If I multiply the world space position by the view matrix, that puts it in the view space. Okay, and what we now have to do is we have to project from the view space to the screen space. Now the screen space is in what we call normalized device coordinates, which range between -1 and +1. Okay, now the simplest form of projection is called orthographic projection, which is defined by a near viewing plane. So here's my camera, we have a near viewing plane, and we have a far viewing plane, and we have planes to the top, right, left and bottom. So anything within this region here, okay, as you can see I'm highlighting with my mouse, that's included in our visible region. Any objects which are outside, so for example this red cube, this is outside of our visible region, this is clipped, so this is ignored. Okay, so the orthographic projection matrix is given here. Okay, so what we're going to do is we're going to calculate this, and I've done this using some code here. So I'm just going to paste this in after we calculated our view matrix. So first we need to define left, right, near, far, top, bottom. So they're essentially the coordinates of the boundaries of our visible area. And then I calculate the 4x4 projection matrix. As you can see there, that's given in the lab materials here. Okay. Now, after we calculated the model view and projection matrices, we've got to send these to the shader, to the vertex shader, and to do so we're going to use uniforms. Now we used the uniform for the texture mapping in lab 3, so we're going to do the same for our model view and projection matrices. Okay, so I'm going to paste this code after we calculated all of those model view and projection matrices. So what these do here is these are all GL unsigned integers. These are just handles for the shader uniforms. So I've got 4 shader uniforms here, one for the texture, one for the model, one for the view, and one for the projection. So we've got to get the handles for the shader uniforms, and then we send those matrices to the shader. Okay, so using the GL uniform matrix for FV. So essentially we have a 4x4 matrix we're sending to the shader. What we have here is we have our handle. So for example, model ID. We're only sending one matrix. We don't want to transpose it. And this last input there, that's just a pointer to the first element of our matrix. So what this does is that sends our matrices to the shader. Talking of which, okay, the vertex shader deals with geometry, because we've got our model view and projection matrices all deal with geometry, we're going to have to change it. So what I'm going to do is just copy this vertex shader here, and if I go to our current vertex shaders, you can see it's quite simple. I'm just going to replace that with what I've copied. Okay, so the difference being is now our position, which is our vertex position, is multiplied by model view and projection to give us our screen space position. Okay. Now if I run that code now, okay, hopefully it all runs. Yeah, so it all compiles. Let's have a look, see what happens. Okay, so we got our spinning cube. It's all running good, but it's looking a bit weird. And if you focus on the bottom side, okay, the bottom side should actually be hidden from us. So this is sort of, we're seeing the bottom side where it should be hidden, and if we focus on the top side again, it looks a bit weird. Okay, so something's not quite right. So what we have, or what's being done, is we have triangles or polygons which are further away from us being rendered after near polygons which are closer to us. Okay, so we're having this kind of overlapping thing. Now the way that OpenGL gets around this is something called the depth buffer or Z buffer, and essentially what we do is for each fragment, the Z distance to each fragment is checked, and if that Z distance is less than that already used in the Z buffer, we replace it. Okay, good news is we don't have to worry about that. It's quite easy to apply. So to apply the depth test, we just insert this code further up. To be honest, it could really go anywhere, but I like to put it as soon as we've created the window. Okay, so what this does, it tells OpenGL that we're using a depth test, and what we also need to do is the start of each frame, so in our render loop, we have to clear our Z buffer. Okay, so I replace that code. Okay, so where this first one clears the color buffer, and this second bit here, this clears the depth buffer. Now if I run that code now, you can see we have our cube, and we're not sort of seeing through the cube anymore. It kind of looks solid to us. Okay, so we got a revolving cube. What you may notice here is we have no depth information. So where we have, so if you focus on this top edge, which is furthest away from us, that should be smaller than the front edge, but at the moment it's the same size. This is because we've used orthographic projection and not perspective projection. So perspective projection is used to give us an idea of how far away something is. The further an object is away from the camera, the smaller it should be. Now with perspective projection, what we have is we have our near plane, and our near plane is defined by the distance from the camera along the z-axis to the near plane, and left, right, bottom, top boundaries for that near plane. Now the far plane, what we do is we draw projector lines from the camera through the four corners of the near plane to give us the boundaries of the far plane. Okay, now this gives us what we call a shape called a frustum, which is kind of like a pyramid with the chop curve. Okay, same as before, and any objects which are outside of our visible area are clipped and ignored. Okay, now I'm not going to go through that here, how this is derived, but this is the perspective projection matrix. So we have near and far, which we decide upon. It's also determined using what we call the field of view angle. Now that's the vertical angle between the top and bottom viewing planes. And we also have aspect ratio, that's the width to height aspect ratio of our window. Okay, so what we're going to do is we're going to calculate the projection matrix, and instead of using orthographic projection, which we've done previously, we're going to use perspective. So what I'm going to do is I'm just going to comment out all of my previous projection calculations, and I'm going to paste in perspective projection matrix. Okay, so here we have, we've defined right, top, near, far, field of view angle and aspect. So in this case I'm using a 45-degree field of view angle, which we need to convert into radians. My window is 1024 by 768 pixels across in the horizontal direction and up in the vertical direction. So that gives us our aspect ratio. Near, well, this has to be some small number. It can't be 0, it has to be positive, but if we set it too large, we'll have some weird clipping effects going on. So I've set as near to be quite a small number, and far is just some large number. So in this case, 100. So anything further away than 100 from my camera will be clipped. Okay, the coordinates of the top of the near viewing plane is calculated by near times tan of half FOV, and the coordinates of my right hand edge are calculated by aspect ratio times top. This code here, that just calculates the projection matrix. Okay, so if I compile and run the code now, as you can see, it's subtly different, but if you concentrate on this top edge here, you can see it's slightly smaller, so the front edge appears larger. Okay, but in a minute we'll plot multiple cubes, and you'll see what I mean, where cubes being further away from the camera will appear smaller. So that works. Okay. Quick note about changing the field of view angle. So this field of view angle can be used to zoom in and out. So if I just run that again, okay, so the field of view angle was 45. Let's drop that down to 15 and run it. You can see it appears like we're much closer to the cube. We're actually, the camera's not closer. It's just the available space which we can see is just being reduced. So this is the effect of zooming in. And if we change our field of view angle to a larger angle, say 90, and our cube looks a lot smaller. So it appears like we zoomed out. So this is a little trick which computer games use to sort of zoom in and out if you've got something like a telescope. Okay. Okay. Now all of the calculations we've actually done manually by hand, but GLM has some code. These are already defined. So for example, GLM lookat calculates a view matrix, and GLM perspective calculates a perspective projection matrix. So what we can actually do is replace all of that code where we actually did it ourselves. So I'm just going to comment out where we calculated perspective and where we calculated this view matrix. Okay, and I'm going to replace it with the GLM equivalents. Okay, so you can see here, calculate the view matrix. So the inputs of the view matrix are the camera position, the target, and world up. And calculate projection matrix. So all we need is FOV, field of view angle, aspect, near, and far. And if we run that, you can see we've got exactly the same result. Okay, so moving on to plot more objects. Okay, so we're going to add some more cubes to our 3D world. So I'm just going to copy and paste this code before the render loop, just down here. Now what this is, I've got 10 three element vectors. These define the center points, or where I want to move my cubes. So this first cube is at 0, 0, 0, second cube is at 2, 5 and minus 10, etc. Okay, and now to draw my cubes in the render loop, what I need to do is, before I calculate the view matrix, okay, so if you have a look at this for loop, I've looped through our 10 cubes. Now the model matrix is going to be different for each cube. So the cubes are translated by whatever the ith cube position is. And I think I've also I'm rotating them based upon the value of I as well. Okay, so if I run that, oh, I got some. Yeah, I got some errors here. That's because we're missing out on the. I think I've commented out the handles somewhere, haven't I? Where have I? Oh yes. So what I'm going to do is I'm just going to move these handles to before the for loop. Okay, let's see if that works. Oh, and I'm missing out on something. I know what's happened. What I should have done. I'm just going to undo. Okay, so what I've done is I've undone. Oh, not quite yet. Just undone that pasting of the for loop, and I'm going to put it down here. Oh, I've got this. Right, let's go back again. Let's copy it. Where have I calculated the model matrix? I'm going to paste that there, and I'm going to comment out this code. Let's see if that, yeah, it works. Okay, if I run that code, oh, that doesn't look quite right. I wonder what's gone on here. Bear with me. So, and draw the arrays. So something doesn't look quite. Right, that shouldn't be there either. Run that. Again, we're a bit too close. I think what I haven't done is change the position camera. So I haven't quite done this yet. So I need to change the position to 005. So where I calculate the view matrix, camera position was at 110. So if I change that to 0, 0, and 5, and run that, there we go. So you can see I got multiple cubes. Okay, so this cube has stayed in position, but this cube up here, okay, this is in the distance. The actual cube size itself hasn't changed. It's just because it's further away from the camera, so it looks smaller. Okay, so that's the so we calculated the model matrix, calculated the view matrix, and calculated perspective matrix, and applied it. That's, if we have a look at our code, it's starting to look a bit messy. Okay, we've got lots of code here. Now this normally kind of hints at the fact we should factor or refactor our code. And what I'm going to do is I'm going to create a camera class. Okay, so what I'm going to do is just copy this. And if I go back to Xcode, okay, so I'm going to create a class for all my camera calculations. Okay, so to do that, I'm going to add a file, C++ file, and I'm going to call it camera. And I also created a header file. Make sure it goes in the source folder. Okay, and create that. Okay, what I like to do is keep all my header files under here. Okay, so create in my header file, I paste in that code from the lab materials, and so what this does, it creates a class called camera, and camera has some attributes. It has the projection attributes, so field of view angle, aspect ratio, near and far. It has a camera vectors, the camera position, camera target, and world up. It also has the view and projection matrices. And so the constructor, what it will do is it will create a camera object, and it will initialize it to whatever position has been stated. Within the camera class, we have three methods: get view matrix, get projection matrix. Now both of these will return the view and projection matrices, and I've also got another method here which will calculate the view and projection matrices. Okay, so, and to go into camera.cpp, so this is where we're defining all of our methods. Okay, so you can see here's a constructor. So position is initialized to position, so that's given by the input. And target and world up are just initialized, so target is default is 000 and world up is 010. Okay, get view matrix, well that just returns view, and similar for get projection matrix. And within our calculate matrices method, we calculate the view and the projection matrix. Okay, so now what we need to do, so if I go back to the materials, so the first thing we need to do is create a camera object. Now this is done before the start of our main function. So all the way back up to the top here. Okay, so I'm going to create a camera object, and you can see this camera object is created and its initial position at 0, 0 and 5. And now when I calculate the view and projection matrices, I've just got a couple of lines of code. Okay, so I can tidy up our codes. Actually, I'm going to delete all of this now. We don't need it. Okay, so where we have the we need delete that as well. We don't need model matrix. So instead of calculate view and projection matrix, I can replace that with our calculate matrices method, calculate view and get view and get projection. Okay, so if I run that now, oh, it's failed. So I'll tell you what I haven't done is if we check out the error, unknown type name camera. Okay, the reason for that is I haven't included my class, so I need to include camera.hpp. Compile that and it runs, and if I now run that, we can see we have the correct result. So that camera class, what we can do, and this is done in the next lab, is we're going to change this camera class so that we can use the keyboard and mouse to move our camera around.